Hi everyone, this is Bruce from the Hong Kong Polytechnic University. In this work, we introduce a model called GLA-GCN for the task of 3D human pose estimation from monocular video. Before I get started, I would like to provide the agenda that this presentation will go through. First, I will provide the introduction and related work. Then I will introduce the proposed method, followed by experimental results and the conclusion. 3D human estimation can have a broad application scenarios such as smart city, healthcare, manufacturing, and so on and so forth. 3D human pose can be retrieved from the motion capture, which is very expensive and usually hard to set up. Instead, we can detect the 3D data by using a monocular video camera, which is a more widely used sensor in our daily life. But it is faced in front of several challenges, such as the flexible body configuration, the diverse body appearance, and the complex environment. The contribution of this work can be threefold. First, it proposed a model to leverage the global and the local representation, and which contributes to performance. Second, it is the first to introduce an individually connected layer that utilizes the independent structural feature of GCN model for the task, which is different with the fully connected layer utilized in prior works and brings new insights to the GCN model. Lastly, it outperforms state-of-the-art methods by using the ground truth 2D pose data on three popular datasets. The existing works can be grouped into model-free and model-based methods. 2D to 3D lifting is one of the model-free methods that needs to detect the 2D pose. The advantage of the lifting method is that it can take advantage of the improvements at the 2D pose estimation methods, and it reduces the data volume and the complexity of the task. And usually, the 2D to 3D lifting methods can outperform direct estimation approaches. Existing methods working on the 2D to 3D pose lifting can be grouped into TCM-based methods, GCN-based methods, and transformer-based methods. Our method utilizes the strategic design in the TCM-based methods and also utilizes GCN-based methods by making good use of its independent structural feature in the GCN model. So the goal of our method is to estimate the 3D pose from a sequence of 2D pose data. So globally, we represent the 2D pose sequence by using an adaptive graph convolutional network. So we utilize several GLA-GCN blocks to reconstruct the 3D pose sequence first, which is optimized by a global loss, and then we shrink the feature along the temporal dimension by using several layers of the stranded GLA-GCN modules until that the feature is shrunken to the size of 96 by 1 by 17. After we got the shrunken feature, we then proposed the individually connected layer, which is implemented by an unshared and shared implementations. So for the unshared implementation, we utilize different convolutional layers for different joints, for different joint features for the estimation. For the shared implementation, we utilize a single shared convolutional layer to estimate the 3D pose of different joint positions. And our model can be optimized by two stages. In the first stage, we optimize the global and local loss together. And in the second stage, we utilize a refined module proposed by PSTMO to optimize the local loss. Our method is evaluated on three popular datasets by using two evaluation metrics, Protocol 1, mean per joint position error, Protocol 2, pose align, and MPJPE. According to the results on the human 3.6M dataset, our method achieves the state-of-the-art performance by using the ground truth 2D pose data. However, our method underperforms state-of-the-art methods by using relatively low-quality detected 2D pose. We also observe similar ranking in the second evaluation protocol, PMTJPE. Regarding the learning progress, our method can converge very quickly at both two stages, and the model size of our model is relatively larger than the state-of-the-art method. Regarding the visualized results for the qualitative evaluation, our method can outperform state-of-the-art method mixed STE for most scenarios, but occasionally it can also underperform this method. So let's take a look at the feature before the individually connected layer. So intuitively, that for the eating action, the two hands should be the joints of two hands should be more similar to each other, while for the walking action, the two legs should be more similar to each other. As we can see from the interjoint feature cosine similarity matrix, we can observe this similarity by using our individually connected layer, but did not observe this by using the fully connected layer, indicating that our method can effectively contribute to the performance. We also achieved the state-of-the-art method on the other two datasets, especially by using the ground truth data, which is significantly outperforms the state-of-the-art methods, indicating that the 2D pose quality is very important. We also ablated the three key designs of our model, the GCN strategic design and the individually connected layer, and we also degraded the quality of the 2D pose feature evaluated of our method, and also shows the importance of the 2D pose quality data. Our method has its limitations. Firstly, it underperforms state-of-the-art method on the detected 2D pose, and the model size of our model is relatively large. In the future, we are going to further investigate these limitations and consider the independence at different layers instead of just the last layer. And we're also going to expand our model to handle 3D human pose estimation at a wider environment.